It's time, I think, to start, so we will just do exactly that. So first of all, welcome to the first afternoon session. This is about the Web UI chapter, the Advanced Web-Based User Interface chapter of FIWARE. And we will do the presentation together. My name is Philipp Slusallek. I'm a professor for computer graphics at Saarland University in Germany and scientific director at the German Research Center for Artificial Intelligence, where I lead the area of agents and simulated reality. I'll give a quick overview and introduction, and then Torsten Spiedelnner will take over, who is the architect of the Web UI chapter. And he will tell you much more about the details, the different UIs, the different GEs, and how they work together and what you can do with them. So, to get started, we have these different chapters in FIWARE. You've probably know quite a bit about the general setup of FIWARE. And in the following, we'll focus on the Advanced Web-Based User Interface chapter. In terms of the details or the architecture of this chapter, the objective is to significantly improve the user experience in FIWARE. Obviously, we all know that user interfaces today are, to a large part, in particular if you talk about web-based or service-based developments, user interfaces are in many cases actually implemented through the web browser in HTML5 and things like that. And there is a strong continued development on that side. But that is mostly focused on 2D user interfaces, as we all know them. What we're focusing on is building on top of that, extending that. So in the web, we already have video. Of course, we have text in various formats. We have images. We have audio. But we didn't have really interactive 3D graphics. And this is what we're focusing on here, really integrating interactive 3D graphics directly in the web browser, and also allowing this to be shared so many people are distributed across the world connecting to a shared 3D experience. And that 3D experience is really not a separate entity, but it is part also of a 2D. So it could be a 2D, 3D experience, and the 2D part and the 3D part are part of the same web document, of the same web page, using exactly the same web technology. Actually, we implemented all of the stuff you will see today in JavaScript without any extensions or anything. All of the technology for doing this is in current browsers already. And Torsten will go into a lot more detail here. In addition to the core functionality, there's a number of additional generic enablers in this chapter. Well, maybe quickly go through that. So we have the, where's my pointer here? Here it is. So we have the core, the server core of the GEs, which is essentially synchronizing different 3D experiences. We have the client core, which is really the part that runs in your browser and enables all of the functionality. And then on top of that, we have client-oriented generic enablers, virtual characters, interface designer, and in particular augmented reality, and we'll show some examples of that later. And then on the server side, we have some supporting generic enablers for displaying geographic information data as well as point of interest data. And you will learn more about that later on. We also have rendering on the server side rendering as part of this architecture. And so in the following, we will talk about the core technology here on the server and the client side, and we'll give you a little bit of insight about some of the additional GEs that we have developed in this area. And with that, I hand over to Torsten, who will show you all the details and some of the demos.
Okay, so thank you for this introduction. And from here, I will dive directly into the details of our chapter. As Philipp already pointed out when talking about user experience in the web nowadays, this covers already a wide range of different media types. There is not only text anymore on the web pages as it was in the early days, but there is also multimedia content like videos, there is audio, there are interactive elements, and moreover the web pages are no longer static, but a wide range of the content that is available on the web is nowadays created by users. So sharing content and publishing content that is user-made is also a big part of nowadays web experience. As a result, many types of standalone applications which were formerly implemented as applications that ran on your PC have now moved to the web. So popular examples are, for example, email clients, which are now available as webmail, but also collaborative text processing, which you also often use here in terms of Google Docs, for example, but also image and video editing tools, which are integrated in platforms like YouTube, but also Facebook or others. And dimension, which is a bit underrepresented, maybe not underrepresented, but not as easy to realize nowadays, is 3D visualization, even though it provides a compelling set of use cases also to extend the experience even further. So applications like smart city visualizations, interactive smart city applications, visualization of IoT data, also visualizations in terms of robotics, also talking maybe about prototyping of new building parts. All this can be enhanced by 3D graphics, obviously. And actually 3D graphics in browsers are already available for quite a while. So the goal is not to create 3D in the browser for the first time. This came with WebGL some years ago and has become so popular in the meantime that also recent game engines, for example, target the web browsers as application platform or as target front-end for client applications. However, creating these 3D applications with the given tools, be it directly against WebGL or using the game engines, this requires quite a deeper knowledge and also some experience in 3D application programming. Especially if you implement directly against WebGL, it's very close to the GL programming. But also if you use these provided game engines and the deploy mechanism there, you will have a steep learning curve and also some considerable effort, even for the smallest applications. Now, what we're doing in the Web UI chapter is an approach to solve this and make 3D graphics more accessible to designers and people who are more familiar with web design, is to describe the 3D scenes and 3D applications in a declarative manner directly in the website. So the idea is that the 3D UI XML 3D generic enabler, which provides these capabilities, extends directly the HTML5 node set, so it introduces new nodes to describe 3D scenes directly within the web page with the common tools that are familiar to web designers. And this includes new nodes to describe 3D models, but also the materials that are attached to the models, the respective textures, lighting of the scene. And the nice thing is that the way it is implemented, namely as JavaScript library, it runs directly in the browser, so there is no plugin needed in order to display these 3D scenes. But every modern common web browser is able to display these declarative described scenes. And moreover, by embedding it directly into the web page, we can also use the capabilities of existing services, especially those from FIWARE, which provide interfaces to web applications to directly link these services and the data provided by the services to these 3D scenes. In the following, I will give a short insight in how this can be done. First, here is a very short example of how such a 3D scene in the browser looks like. So for those of you familiar with web design, it's basically nothing more than a standard web page. The new nodes can be found here. It's basically the XML 3D node, which encapsulates the whole XML 3D scene, and everything which is included within these tags now describes our 3D scene. Here, for example, nodes to define transformations. You have grouping nodes which allow to group different models and apply, for example, a common transformation to them. And you can, I lost my mouse pointer. Also reference external data, for example, this cube JSON will then contain vertex and normal data that describes a cube 3D model. And the nice thing is that this is not entirely in format particular to XML3D, but it supports various formats. You can link a JSON representation of 3D models, XML representations, but also GLTF or Collada models. There are a few exporters which allow also to export to the XML3D format. So if you have some model existing in Blender, you can run an exporter over it and integrate the model in your web page. For more complex scenes, XML3D provides an asset mechanism. This means even quite complex structured models can be hidden behind an externally referenced web page. You can instantiate them with one single tag, which resembles very much integrating an image into a website. You can make quite complex definitions of your assets in an external file, and then by one single tag also instantiate this model within your scene. You see two examples here of different use cases. Here, for example, this might be how a multi-user application looks like. In this case, every user is an instance of such a robot model, or also in collaborative 3D editing tools, you would be placing instances of predefined 3D models directly into your scene. Now, so far for static scenes, in order to bring interaction to it, there are different interfaces to modify the scene during runtime. So the most convenient way is that there are directly HTML events registered on the XML3D nodes. So whether you have a model or an asset or a mesh in your scene, you can register on mouse over and on click events, as you would do it also for images or paragraphs in your web page, and by this directly profit from the interfaces that HTML gives you. There's a JavaScript API for more complex scripting, and this can also be used to create or modify new nodes in the website's DOM tree. By this, extend your scene, modify your scene, or also build a connection between the 2D content of the web page or the 3D content. And a benefit from that these XML3D scenes are basically part of the website and its DOM is that we can use established frameworks like jQuery or Backbone.js or others to query the scene or to modify it. And I have a very simple example here. So assuming we have a cube already existing somewhere, the one I showed before that has an ID that is called cube, we can use jQuery to find this cube in the scene, and by just changing the attributes of this node, we can apply new transformations, but also new shading information. And in the same way, we can also create new elements and just add them to the DOM. So this is very much similar to how you would also create 2D elements or static elements in existing web pages. For more complex computations, we have a tool called XFlow. The name comes from the fact that it's basically a data flow description that is directly integrated in the XML3D implementation that we provide. So data flow description language means we have a set of input parameters that we can define. These can, for example, point to services that are deployed in FIWARE, context broker, for example. And then based on this input data, a set of operators is run, and the result of these operators is piped back in our scene, and by this changes our scene dynamically. The nice thing is that the XFlow data flows can be computed on GPU, so they can be computed efficiently, and for this are highly suitable for complex tasks like character animation, which performs some skinning animation on the models, but we can also map input data from IoT sources, for example, to our scene. By this, apply vertex transformations or shader transformations, and, for example, change the height of these bars, assuming that they maybe represent pressure or temperature in a 3D map. And we can adapt the height and the color and maybe also the shape of these models according to external input data. And by this, the whole framework XML3D with XFlow and the JavaScript interface provides a compelling tool to add information visualization to our 3D scenes. Now, so far we've seen the version of XML3D that we are providing in FIWARE currently. The future development, which we are currently working on, targets at exploiting the capabilities of web components, which is a new concept that is implemented in the latest browser versions, becoming more and more accepted. And this allows to, on top of these generic grouping and mesh and light nodes, also define custom nodes that encapsulate more complex and user-defined concepts. So we have seen these robots in this multi-user scenario before. So we could, for example, also define nodes which says we have an XML3D robot here, and the node provides us an interface to the values that we need to modify, for example, animation or shading of the robot. A small example is down here. So this is how, for example, a teapot could be described as a web component. And instead of instantiating a teapot mesh and doing the transformation manually, we could just define that this node knows about its scale and its color, and by this modify the model accordingly by just adding this node to the DOM tree. So to sum up the 3D UI generic enabler so far, we've seen that it allows us to create interactive 3D graphics in web applications by simply extending the HTML5 web page in which the 3D application is running. And by using the web or the DOM interface as well as JavaScript and Xflow, we have plenty of options to also link the 3D graphics that we create in the static scene dynamically to external services and also application-specific data, which may come from a use case in a FIWARE scenario. Now, one generic enabler that does this, for example, already is the augmented reality generic enabler. This one uses 3D UI XML3D and the connected Xflow capabilities in order to implement marker feature and marker tracking operators directly in XML3D. And by this, we can, for example, detect this kind of markers, which most of you may have seen before, and by this position the 3D objects also in our scene, or change the orientation or animation of the objects. And in one of the FIWARE hackathons, this one was actually also used to create a nice web game which spawned 3D spaceships from street signs. And by this, you could walk a city and collect your high score on different street signs of the city. Another use case from the visualization field, which is also encapsulated in a generic enabler in the Web UI chapter, is the Gis Data Provider. This one provides elevation datasets from different regions in the world in different formats. You can query the provider using a REST call. You specify your geolocation in longitude or latitude. You specify the format. And as a result, you get an XML3D chunk, an XML3D tile, which directly visualizes the 3D map at this area that you specified. So basically, as a resource that you link to your 3D scene, you can specify this location on the Gis Data Provider, you query to the Gis Data Provider, and by this assemble your 3D map from the data that is provided there. And with an additional generic enabler from our chapter, the PUI Data Provider, you can run the same query, the same longitude, latitude-based location query on the PUI Data Provider, and in addition to the 3D visualization of the map, you will be provided with all the points of interest in this region. And attached to these points of interest, you also can specify a 3D representation of the object, either as XML3D resource or as raw mesh data, and have your PUI also visualized in 3D directly on your 3D map. So far, these have been single user applications, so we've seen how to create 3D maps. We have seen how a single user in the web browser can inspect the 3D scenes and interact with the 3D scenes. What is missing at this point is the question, how can we share a 3D scene among multiple users? So how can I not only interact with the 3D scene as such, but also with other users who are part of the same 3D scene? There are plenty of use cases for this scenario. Very popular, possibly the gaming scenario, but also social platforms in which members of the social platforms are represented as 3D avatar, but also training applications with different roles in training scenarios, and also collaborative work scenarios, CAD work, for example, or 3D design. And the solution for this in our chapter is what Philipp introduced earlier as the server core of the Web UI chapter. And this is basically provided by the Synchronization generic enabler. And I will in particular highlight the implementation 5s here, because it's the one with the latest release in the chapter. The role of it is to, or let's maybe start like this. If you want to provide a multi-user environment, the most common requirements are that there needs to be a consistent world state that is to be stored somewhere in the network, either on the different nodes connecting to the application or on a server node that is running somewhere in the cloud. And as soon as the clients connect to this world, they get the recent world state, which is depicted here, so they have an immediate insight into how the world currently looks like. And as soon as some node changes the state of the world, the state needs to be, of course, transferred to all connected clients in order to end up with a consistent world state in all connected applications. And very often, especially in gaming, but not only in gaming, but also in these social platforms maybe, there's a, let's say, soft real-time requirement that as soon as one node changes the status of the world, it is immediately transferred to the other clients, so they always have the same state of the world. Now, the synchronization generic enabler, in order to be as generic as possible and easily adaptable to different application use cases, is a very lightweight server implementation in the sense that it tries to make no assumption about the actual application data from the beginning, but rather provides an extendable component system, which I will show a bit later. The data in the server can be queried either by a REST HTTP request via a Scene API, and there is also a WebSocket communication for real-time synchronization to connected clients. And the main target clients are web browsers, in particular, of course, also the 3D UI ones we have seen a bit earlier. Now, within the, maybe to get the whole image of what synchronization then does in the role of FIWARE, is that we have a number of scalable backend data providers. We have the context broker. In the last session, we have seen the IoT broker. We have seen different IoT gateways to connect to. And these provide access to data for large-scale complex applications. For example, city visualizations, which we have also addressed shortly a bit before in the 3D UI city. And now what synchronization does, it allows to offload the computation of these applications to some node in the network and not have the browser-based clients do all the work, but we pre-compute the world state. We provide it in a model, in a data model that can be interpreted by the 3D UI immediately, but also by other visualization clients. We can run simulations on the data and send data based on simulation to the clients instead of the raw data. We can filter the data. We can do all this before we send it back to the clients. And by this, we consider, and this is actually how we used it quite often, this synchronization generic enabler in our applications, as a bridge between the data that comes from outside or that comes from somewhere within FIWARE, a bridge between this and then on the other side, the web UI front ends and the clients. So the very high level architecture looks like this. I've mentioned it shortly before already. We have the server, which provides the RESTful Scene API, which is not necessarily meant to be compatible to the real-time requirement. It can be, but doesn't need to be, but is more for external access and one-time modifications like external editor applications or one-time queries to just get the current world state. And then on the other end, we have the real-time sync protocol, which is based on WebSocket, which always immediately transfers new world states to the client. And of course, this HTTP interface is basically meant for CRUD operations to modify the internal scene model, adding new objects, modifying existing objects, or asking for the state of objects which are already there. Now, the data model we are employing is an entity component attribute model, which of course also maps quite nicely to what the context broker provides us. We have also seen examples of this in previous talks. So the idea is that the objects we have in the world are basically just empty data containers from the beginning, and the actual meaning and the data that these objects carry are defined in the terms of components. For example, if some object in our world should have some 3D location in the world, we would attach a location component, and this one carries the data of the 3D location. The nice thing is that these components can be defined and assigned during runtime, so this means we don't need to recompile this server when we want to attach a new application, but we can just introduce new data structures while the server is running. We can deploy a new instance of the server to the FIWARE lab, for example, without changing anything to the code or needing anything to compile, and just introduce new components while the instance is running. This entity component attribute model, as I said, maps quite nicely already to what we get from the data providers. Here's an example of how a POI could look like in the synchronization representation. This would now be an entity which is identified by some universal identifier, and then we have different components which describe the capabilities and the role in the world. So in this case, it carries a component to describe its location in latitude and longitude, so this one would be suitable for geovisualization. It also carries information about how we would visualize this entity using the XML3D generic enabler here. So we have here an asset that would be rendered for this one, and also different configurations of which input data we would map to which output parameter. And FIWARE's, the synchronization generic enabler implementation, also supports NGSI v2 formatted messages, so we can directly exchange messages, for example, with the context broker using the NGSI v2 format. This is how data maps from backend to server, and now the mapping from server to frontend is equally simple. So we can basically directly fetch our components that we define on server side and map them to 3D UI DOM nodes in a model view manner. So here is an example of how this might look like. We have an entity with a mesh, transform, and material component. So this means this entity has some transform in the 3D world. It carries information of how the 3D representation of the entity should look like, and also some material. And these would be the respective nodes that we create in the XML3D generic enabler. And we are not limited to this representation if for some reason we changed the way how we describe transformations and meshes or switch to a different 3D render framework. We could also map it to a different style of nodes. So on the above image shows a bit of how our example application does all this. We have the model layer, which retrieves the entity collection from the server. We have the controller layer, which basically arranges the entities in the client representation and also checks for the externally referenced resources. So if we define a mesh here, this part of the application knows where to look for this mesh, and then this one basically submits the data to the XML3D scene, which is then composed of the nodes we have seen in the beginning. And here we see a few of the applications we have built with synchronization in combination with the 3D UI generic enabler. We had this multi-user scenario from the beginning. We had also some visualization of factory modules. So in this case, we got information about pressure and velocity of certain parts of this module and turned it into animations for this scene in order to estimate of how the factory would work like in the real scenario before actually implementing it. This one builds on this one, so it basically uses the same world, but adds information that can be used by AI agents, which then interact with the scene. So this adds the factor of human workers and allows to estimate how efficient this factory might be handled by human workers. And the last one is a dual reality application in which we had a factory setting with different kinds of robots, and these interacted with the human workers, and we could not only see what the on-site situation was in the 3D visualization, but we could also use the 3D visualization to steer the robots in the real world. And going from these multi-user scenarios to 3D map multi-user scenarios is then a simple task, because all we need is a component that describes the role of one entity in the world as a geopatch, and we use the capabilities of the GIS and POI data provider that we have seen earlier in order to create also entities from these query responses on server side, which are then in turn rendered in our 3D visualization on client side. And in this example application here, which was shown on the ACFI conference, I think we also used some Xflow operators to extrude buildings from OpenStreetMap data. So to sum up the talk, we've seen how 3D graphics can enhance the experience of existing web applications, which already bring a wide range of different multimedia types. But by building heavily on the existing HTML5, the 3D UI enabler makes the creation of the 3D web apps also accessible for web designers and people not being too familiar with 3D graphics implementation. And not only static 3D scenes are possible, but also interaction can be added quite easily by adding, by making use of the standard HTML events. Apart from this, we can link our 3D applications to arbitrary data sources. On the one hand, using these model view patterns I have quickly highlighted with the synchronization generic enablers, but also with the capabilities of Xflow and JavaScript, we can use established HTML frameworks to modify our scene after it was deployed to the browser. And we have seen how to create examples of the domain of geo-visualization, and also how we can serve multiple clients in a shared environment with the synchronization generic enabler. Which uses a generic data model, this entity component attribute model, which is easily mappable to both backend data, so we can connect to different data sources, but also to the 3D UI scene graph, which means we can directly bridge from the data source to the client using the synchronization generic enabler. And by this, synchronization provides the bridge between FIWARE data backends and multi-user 3D front-end applications. So this concludes the talk. I would now show a few demos, demoing mostly the 3D UI generic enabler, and afterwards I would say we move to the questions. So the first demo is quite simple. So what we see here is the 3D Rubik's Cube. This is rendered using the 3D UI XML3D generic enabler. So this whole cube is a DOM object, basically, an object that lives in the web page. Same for all the surfaces. And you see now interacting with the scene is as easy as registering, for example, an on-mouse over event on the surfaces. This is what is done here. It's just part of the web page, so this is possible, and we just change the shading of this. We can also interact with the scene and rotate it, but we can also use other events like on-click to just interact with the cube, select one of these parts of the cube, and also then play this Rubik's Cube game, which is, I think, quite well known. I have also talked about using Xflow for skinning, so this actually works. Here's an example. These are 3D meshes which are provided with a skeleton, and this skeletal animation is then computed using a skinning operator provided by Xflow that can just be applied to these 3D models. And as a last example from the domain of construction, maybe. So this, Philipp, correct me if I remember it wrongly, was in cooperation with the UCL, London University of and the idea here was that during the rework of the King's Cross station in London, there's also a 3D model which allows to inspect the new station before it is actually built. And this actually shows that we can not only create these toy examples, but that the generic enabler is actually also capable of displaying really large scenes of how many million triangles were these?
I can't remember. It's several million polygons here. Maybe you can fly into the building.
Yeah. So it's not just the roof, and you see it's also quite detailed in the inside.
People who've been through King's Cross Station, this is pretty much what it looks like today.
Okay, and this concludes the presentation at this point. And we're open for questions.
Yes, are there any questions we can answer? Everyone's overwhelmed. Thank you.
With the Xflow part, is it possible to gather or add depth data, say from external sensors, or maybe capabilities
execution on current CPUs. So they have these SIMD extensions, SSE and AVX. Intel and others and the browser vendors are currently teaming up, or actually it's in the beta versions of the browsers already, to be able to use these SIMD instructions. And we're getting a speed up factor for some of the computations of more than a factor of 3. In JavaScript, we write the code still in JavaScript, but we optimize it in our engine. That is not in the current version of what we deliver, but that we plan to make that part of FIWARE in probably within the next year. I can't make any promises yet, but it's something that works internally already, but still needs some more work, and it's not in the browsers yet, so we have to wait until Firefox and Google, Mozilla and Google make that available. But you see, oh, actually, can you show the augmented reality?
Right.
Because that actually goes into your direction, I think.
Right, this is here somewhere. I forgot this one. Flying TP.
By the way, this webpage here is off of our XML3D webpage. So you can actually just go there and play it in your browser as well. You need a WebGL enabled browser. There is still a few out there that are not WebGL enabled. Sometimes some older laptops, the hardware is not up to the. So what you see here is actually there's a video running in the background, and the video contains some of these markers here. And the application logic says, okay, on top of that marker we have a teapot jumping up and down. And so the orientation of the marker determines in which direction the teapot jumps. And this is, so the teapot is not in the video, right? The video does not contain the teapot. We just show the video here, and then online in real time we detect the marker. So this is like your depth computation. So we do marker detection on the running video in the client in JavaScript, and then once we detect the orientation, we render the teapot on top of that relative to the 3D position of that marker, which we reconstruct from the video. And just to prove that this is not in the video, we can actually switch to the camera, and so this is Torsten, and if the lighting conditions are just right, you will see that there is a virtual teapot jumping up and down on top of what Torsten is just showing there. And you can also maybe show both.
Let's try. This one was a bit stubborn before.
Maybe move it a little bit further away from the camera.
It's a bit broken on the edge. Maybe this is the problem.
Right. So maybe we need a little bit better lighting for that. So this is not a production demo, of course, but it kind of shows what can be done with the entire framework, including augmented reality. Actually, to add to that, there is, so I co-organized with the W3C. W3C is a World Wide Web consortium which standardizes all of the HTML stuff. And there was a workshop about 2 or 3 months ago, in San Jose about WebVR. WebVR is essentially technology that the browser vendors are developing internally right now for attaching the Oculus Rift, the Vive, and all of the other VR headsets directly to the browser. And so the idea is someone sends you a link, you click on the link, the browser opens, and you're right in the 3D scene automatically. With your VR headset, maybe in the future even with augmented reality headsets. And that's something, so that was like a kickoff event for this development. This is being driven now by W3C on the one hand side, and Kronos, which does all of the 3D optimizations, 3D standardizations, I need to say, on the hardware and low-level software side. So there will be a lot of development in this direction also in the next year, or maybe a little bit longer, depends how long that will take. So I think this is very, very exciting technology. We can directly drive that. So in-house, we have already a prototype implementation of WebVR for some of the beta versions, 90 versions of the browsers that already contain an early implementation of that. So this already works versions yet, but that will be coming hopefully pretty soon. So all of that is directly enabled for FIWARE, and as Torsten nicely showed, that we could directly link that to data providers. That could be IoT data in the city environment. We could link that to smart city implementations, all sorts of other things for visualization. We have shown a number of demos in that direction already. There's lots of examples and other stuff on our webpage if you want to see more. But there's more questions.
I believe it won't be a problem to add also simulation algorithms in this procedure. For example, let's say that I can see how the suspension system of a modern car works.
Absolutely.
And change the terrain and maybe take actual terrain and see how it works, but after computation of a simulation algorithm.
Yes, and that's exactly what we do in a number of projects that we can't show here because they're usually industry projects where we have some simulation code somewhere, we package that as a service, and then we get updates on the model and display that in the browser, and we can also control the simulation from within the browser. So one of the big projects we're currently doing is kind of doing synthetic data generation for learning for autonomous cars, for instance. Really interesting application. That of course goes beyond what we show here, but yeah, I think this is a really nice use case or scenario of linking simulation code of various, I mean, this could be agent-based, large-scale city simulation, could be like a very mechanical simulation, could be lots of other stuff. And the really nice part is, right here you're in the browser, you can very easily link to these services once you have a suitable service interface. And Torsten kind of showed how easy it is. You just put a link there as long as it provides the data in some meaningful JSON or whatever format. It's very easy to link that to the 3D model.
I believe that this could be very useful for education also.
Yes, we're not doing any educational projects, but we use it for training in industrial scenarios, which is kind of an educational scenario as well. We're not doing anything with schools yet, but maybe others wanted to pick that up. Yeah.
Yes, thank you.
Any other questions?